This is a short video for explaining the Brownian motion as a result of random movement in the physics course for biotechnology degree in the Universitat Politècnica de Valencia. Learning objectives: to identify parameters that define random movement, to describe random movement, to determine diffusion coefficient, to understand the relationship between microscopic parameters that are impossible to measure and macroscopic parameters which are easily measured. List of contents: backgrounds of Brownian motion, description of random movement, determination of diffusion coefficient, discussion of the importance of diffusion coefficient as a parameter that describes random movement and how it can be measured. Brownian motion is the movement that do colloidal molecules immersed in a fluid due to the thermal agitation of water molecules which hit to those bigger molecules at high frequency, but produce a visible movement of these colloids. To understand this random movement, imagine there are 8 particles moving in one dimension. In its movement, each particle can displace an elementary step of length L, as much to the left as to the right, and with the same likelihood, because all particles move in a random movement. We assume that when all particles move from the same position, half of them will go to the left and half of them will go to the right. We will follow 3 random displacements. In the first step, 4 particles move to the right and 4 particles move to the left. In this table, I have written down the final position of each particle after the first displacement. So we have 4 particles that have moved to the right and 4 particles that have moved to the left. The average displacement is 0. It is the sum of all the values of final displacement divided by the number of particles. But what happens with the mean square displacement? We have to add all these displacements but to the square. So we have 4 displacements that are L2 square and other 4 displacements that are minus L to the square. When we solve this, the mean square displacement equals L square. It's different from 0. In the second displacement, half of the particles that were at L move to the left and half move to the right. The same behavior follow the 4 particles that were at minus L. This movement is represented with a dashed line. Here in this slide, I have written down the final position of the particles after the second movement. As you can see here, after the first movement, half of the particles at position L move to the right, so first and second particles have a final position 2L, while the third and the fourth have come back to the initial position. The same for the particles from 5 to 8, that from the initial position half will move to the right, for example particle 5 and 6, and particles 7 and 8 have moved to the left, and their final position is minus 2L. If we calculate the average displacement for the 8 particles, we'll discover that it equals 0 as the average displacement in the first movement. What happens with the mean average square? If we measure the mean average square, we have 2 particles that have displaced 2L, so to the square is this value, and two more that have an effective displacement of minus 2L to the square. The particles that have final position 0, sum 0 here in this calculation. So finally, the mean average displacement equals twice the square L displacement. The third movement is represented in a dotted line. Here we have the same as before. The two particles that were at 2L, half of them move to the left, half of them move to the right. The four particles that were at position 0, half of them move to the left, half of them move to the right. And the two particles that were at position minus 2L, half of them move to the left, half of them move to the right. So the final positions with respect to the x-axis are written down in this table. So the average displacement after 3 movements equals the sum of all the displacements divided by the number of particles that equals 0. What happens with the mean square speed? Will it be 0? We don't expect that. Let's see what is its value. The value of it is this one. So if we add all the values of the displacement and we divide it by 8, we get 3 times the elementary step to the square. Summing up what we have obtained after one displacement, mean square displacement equals L squared. After the second displacement, the mean square displacement equals twice L squared. And finally, after the third displacement, we have obtained 3 times L squared. So, carrying this logic to its end, we find that the mean square displacement after n movements, whatever the number of movements we follow these particles, it will be the number of displacement multiplied by L to the square. N is the number of displacements that a particle can do during time t, considering that the time it takes one elementary step is delta t. When substitute this definition into the general equation, we get a new one, which depends on a new parameter called the diffusion coefficient. As we can see, the mean square displacement in a one-dimensional random walk increases linearly in time, and the proportionality constant is d, which equals the elementary step square divided by 2 and delta t. In a two-dimensional movement with unitary displacements of length L, the mean square displacement is defined as the addition of the mean square displacement in each direction. The mean square displacement in both directions is the same as the mean square displacement calculated for x direction. Therefore, in 2 dimensions, the mean square displacement equals 4 times the diffusion coefficient and time. This result means that even if we cannot see the elementary steps in a microscope, it is possible to measure diffusion coefficient experimentally. Simply note the initial position of a colloidal particle, wait a time t, and write down the final position. Repeat the observation many times. The average of all square displacements divided by 4 and the elapsed time will result in d. And with an enough number of observations, d does not depend on the elapsed time t. The important fact is that the diffusion coefficient is a parameter which relates microscopic parameters such as the elementary step and the delta t with a noticeable and measurable quantity. The question now is, how will the mean square displacement be in 3 dimensions? Calculate it and try to apply it in an example. Conclusions. Diffusion coefficient is a parameter that relates the tiny world, such as elementary step L and infinitesimal time delta t, with the macroscopic world, as it is the mean square displacement that can be seen under the view of a microscope.